Yes, I get it. It's a Friday. We all just want to go and enjoy the weekend. It's finally spring, blah, blah, blah. Woo, yeah, okay, come on. Now let's focus up just for a little bit. We got a few problems to go over, and then we'll be out of our way with those Riemann sums. So, as part of our example set here, is that we have a great word problem with a table of data points. It says here that the following are the readings from a speedometer across 60 minutes, okay? And the tables are filled out accordingly, again, in increments of 10 minutes across, going to these different speeds in miles per hour. Of course, our job now with our current practice is that we will approximate the area underneath this kind of graph or the table, which will be divided into 6 sub-intervals using both the right, left, and trapezoid methods to approximate the area underneath a function. All right, so why don't we get right to it, in the sense that you can notice is that for every 10 minutes, we are jumping over to the next data point. Okay, obviously with six sub-intervals going from 10, 20, 30, 40, 50, and 60, those will be our 6 rectangles, each with a base of 10. Okay, that's good to know that we don't need to worry about any other different base sizes. It is simply just going to be one base across all 6 rectangles. Okay, so with the right sub-intervals here, or the right forming of the summation, we will then choose only the 6 right side. So 1, 2, 3, 4, 5, and 6 going from the right side across those different sub-intervals. Pretty good, because then with that case, with us first doing the right side of the approximation, that would mean that we have 10 as the base going across for all of these guys. Okay, so that means that we get 40 plus 55 plus 10 plus 60 plus 32 plus 45. Okay, so we have all those data points jotted down for us, and that will be something that we should be able to then easily follow along with. Now we have a little bit of a problem here actually, because what we might have noticed before over here, take a look, is that we are dealing with minutes and then miles per hour. If we really were to multiply across, again, minutes multiplied by miles per hour, it wouldn't really add up to anything. So in this case, instead of calling it a 10-minute base, we need to switch that unit back into hours, right? And so instead of calling it 10 minutes, we need to swap it to hours, which of course, the ratio is as follows, of course, that there's 60 minutes in 1 hour, meaning that we would need to then divide the 60 in order to reach back into hours, which is a much larger unit per minute that we have. So we just need to divide this by a nice 60. So we end up with a fraction of 1/6 as the base that will be multiplied across all of these guys. Okay. So with some very easy calculations, just because that these are fairly simple to follow along with, if we make sure that we add everything up. So let's see, for example, we have 10 and then a 2 in the ones place, everything else is a 0. We need to carry a singular 1, so that makes it 9, 10 with the 1 carried, 11, 20, 24. So 242 will be the result of everything inside of the parentheses, and then the 1/6 will be left over outside. Then we can do some very easy division here, meaning that by dividing by the 6 across this 242, we end up with a whole 40 and a 2 out of 6, which to me 40 and 1/3. And remember, now that the units do matter, given that this is the kind of word problem that would ask for it, is that we basically multiply the hours per the miles per hour that we dealt with. So that's 40 and 1/3 miles that has been traveled across our estimation for those 60 minutes. Okay, so that's pretty easy to write down and keep a hold of as we move forward here. So that's here. And with that, we can then take the same idea that the base will be 10 minutes, which then, if we're dealing with minutes here, that's still going to be 1/6 of an hour waiting across each of these guys. But now, of course, with our trapezoid approximation, we are going to group each one of these pairs in twos so that we will then take the average of each of their heights and go across that way, right? So 1, 2, 3, 4, 5, and 6. Again, moving down one time to get a total of 6 pairs of 2 heights. So in that sense, the base is still going to be 1, 6 across all of them. But then in that case, we are now faced with all of the averages of each of those pairs of heights. So for example, we have the 26 plus 40. Those are 2 separate heights for the trapezoid. Again, in our minds, we do need to see that trapezoid shape of something like this. Again, we have 2 heights that we are dealing with, and we must average out both of them in order for us to find that area. So 26 plus 40 all over 2. Then we're going to go down and do the rest. So it's 40 plus 55 over 2. And then it's going to be 55 and a 10 over 2. And then a 10 and a 60 all over 2. And then it's going to be 60 and 32. Looks, we got to continue down here. So 60. Make sure we keep it consistent. 60 and 32 all over 2. And then lastly, 32 and 45 all over 2. Like this. Okay? So we have all of these guys paired up. And so now we will just need to then add them up and get to a reasonable answer. So with this, we can go across, keeping that 1, 6 as a coefficient. And then getting to the first guy, so 2640 makes it 66, all over 2 makes it 33 whole, which is pretty nice. Then we will get the 40 and 55, which we might have to keep off to the side for now, which is going to be 95 over 2. And then next we have 55 and 10, so that's going to be 65 over 2. And then we have 70 over 2, which is the whole 35. And then down here we have 60 and 32 makes it 92 over 2. So that will give us a lovely 46. And then a 32 and 45 over 2 makes it 77. So we'll hold that as a fraction for now, over 2. Okay, very good. So we will then be able to combine all the like terms and we'll save the coefficient for last. So on this next line here, 95, 65, and 77, that will still leave us, unfortunately, with an odd number. But 95 and 65, that will give us by itself already a whole 160. So dividing that by 2 means that we get an 100, it's 160 divided by 2 makes it a whole 80. So then we can combine it with everything else here. So 33 and 80 makes it a 113. Adding another 35 makes it 148. And then lastly, a 46 will then leave us at 194, adding with the 77 over 2. Okay? And so from there, we should be able to just distribute the rest, and we'll see what this turns into. So with the 1/6, this ends up with 194. That makes it a 32. Distributing it, so 32. And then that will make it a 2 left over, so it's 2 and a 6 left over. And then lastly, we'll still add it with the 77 over 12 on that sense. Okay, so now let's just simplify this to make everyone's lives a bit easier, is that the 2 over 6 will then have to become a 4 over 12 to match with the denominator of that guy. So we still have a whole 33 and then a 81 over 12, which then lastly 81 over 12 is going to give us 6, so a whole 6, and then what's left over, a 9, yes, 9 over 12, which will then be just simplified into 3 over 4. Okay, so 6 added to 33 here makes it 39 plus, not plus, well, and, because it's a mixed number now, so it's and 3 over 4 miles. Okay, so with that, that all will be able to check out, except for the fact that I switched this to a 33 for whatever reason. That is unfortunate. We just gotta, that 32 needs to carry over, so that just needs to stay to a 32. Adding a 6 makes it a 38. Gotta make sure to check your work. So 30 and 3/4 miles is the actual case for this trapezoid approximation. Again, it just takes a little bit of additional carefulness and some arithmetic, but that will all be part of the practice that they will look for you to do on this exam. Okay, so as you can see, again, we have something on the legs here where we have the right side approximation going a bit over, the left side approximation going a bit under, and the trapezoid will be just kind of in between the two of them. That is indeed how most of trapezoid approximation will go, because left and right is a pretty big gap on how the bars will show up on a function, while the trapezoid will be kind of right in between both of them in that sense as well. Okay, so that's pretty good for the first one. Let's get to one more, and then I'll kick you out of here so that you can enjoy your weekend. All right, with the last one over here, we've got one more problem where we are asked to approximate the definite integral from 0 to 6 for this function of 6x minus x squared dx, now in 3 sub-intervals for the left, right, and midpoint approximations. So what I'd like to do right now is to start first with a table of values so we can reference off of our heights and our bases. So if we were to get our values for x and then the f of x in 3 sub-intervals would then mean that we need to go across for just 3 heights, or in this case 4 points, ending in 0 and starting in 0 and then ending with 6 at the end, meaning that we only need 2 more points in between, right? So 0, something, something, and 6. Well, that just means we need to count up by 2s. So 0, 2, 4, and 6 are the points that we need to make 3 sub-intervals for the left and the right side approximations. So by filling out with the results of the function inside the integral, we will then get for the second point, so it's 12 minus 4 makes it an 8. With the 4 makes it 24 minus a 16, making it another 8. And then lastly, the 6 is 36 minus a 36, which is 0. Okay. Which, when I think about it, the 26 minus 16 is 24 minus 16. Yeah, that's still, my goodness, my mental math is not showing up right now. Well, anyways, though, we've got what we needed for that. But something that will help us in a little bit too will be the midpoint, meaning that we actually need to go in between each of those. Again, where the midpoint is the heights that are in between each of the points that were set up on left and right. And we need 3 subintervals, meaning that we need 1, 3, and 5. So those will be the heights for those 3 rectangles for the midpoints, meaning that we can then fill out from the table accordingly as 6 minus 1 as 5, then 18 minus 9, which is going to be a 9, and then a 30 minus 25, which is back to 5 again. Okay, those 3 points will be used for midpoint because they will be in between each of the points that were stated for the left and right approximations. So let's get on with it then, with the left side approximation. Understand, of course, that the base going across each of them is going to be 2. As you can see, right, going from 0 to 2, 2 to 4, 4 to 6. The bases of them will be 2 each. So the left side approximation will have a 2 weighting on the outside, and then the 3 heights on the left side of 0, 8, and 8, meaning that we end up with a total result of 16 times 2, which is a 32. Very simple. Okay, and then going from the right side approximation would actually yield something quite similar in the sense that with the same 2 base, right, the length of 2 on each base of the rectangle, we are now going to go this time 8, 8, and then back to 0 again, thanks to the results of our table. So with going 8, 8, and 0, we actually end up with the exact same area as 32. Something to note, of course, is if you were to look at this function, it will be quite a very symmetric sort of downwards parabola curl like that. And so it does make sense that the left and right approximations would actually be equal to each other, because either going left or right side of this will be yielding the exact same results. But let's have a look at the midpoint now in this sense, because midpoint is going to be right in between of those values of 2, 4, and 6, where in that sense we get 5, 9, and 5 that we found out earlier, which is going to be a 19 times a 2, which will be 38 as a result of the midpoint. So this case, midpoint is actually a little bit larger than left and right, because of how we get closer into the actual heights of this function. But maybe for this, we should take a comparison to the actual. So let's add one more point here as the actual integration on what that looks like. Because again, we'd have the actual full definite integral listed out for us. So if we were to really snake this all the way down here, what that integral will look like, well, with all of our great study of integrals, we can easily take our integration here of something like this, going from 0 to 6, okay? And then we can then set up the limits of integration. Thankfully, with that 0, that's going to make our lives easier. But first, we read it from the top down. So starting with a 6 makes it a 3 times a 36, and then minus 6 to the third power, which is going to be the 196. No, not 196. Sorry, it's the 216. Am I losing it right now? No, 216 is correct. Over 3. Okay. Yeah, just got to make sure that all our mental faculties are ready to go on these types of problems. But nonetheless, though, we can then work through this. So the 36 times a 3 will be a 108. And then the 216 divided by 3 makes it a 72. And so we actually end up with 36 as the result of the true integration, or the most accurate area underneath this curve. Okay, very good. So with that, we end up with our solution set of answers that make the most sense, in the sense that midpoint actually is an over approximation of the true integral, while the left and right, although they're same to each other, are now both under approximations to the midpoint approximation method using a Reimann sum. Okay, that should finally conclude it for this part of this series. We still have many more many more topics to go over in terms of the actual points of this series of definite integrals, because as the AP test has clearly shown in some of our live streams, if you have been watching them, is that there are plenty of word problems involving things of this sort, as well as other definite integral related topics. So we'll definitely be going over them next time. But for now, that should conclude it for us this Friday, and we hope to see you again next week.